Welcome to this course Electricity and Magnetism. Last class we have discussed about how a dielectric material behaves to an or responds to an electric field. Unlike a conductor, a dielectric material has no free charge. They have bound charges, means charges are bound to specific atoms and molecules. But when electric field is applied, there can be some microscopic displacement of the charges in the molecules, which result in a macroscopic polarization of the dielectric material as a whole. These dielectric materials, they may contain polar or non-polar molecules. If they contain non-polar molecules, then due to electric field, the center of positive charge and center of negative charge are being stressed of all the molecules, and when they are in one line, that results in a electric charges developing on the two surfaces of the dielectric material. Those are the of course the bound charges, and that results in electric polarization. And if the dielectric material contains polar molecules, these polar molecules are experiencing torque, due to which they orient and tend to line up in the direction of field. When many dipolar or polar molecules, they orient or they line up in the field direction, they result in a total macroscopic polarization in the material. So today we will discuss about this behavior of dielectric medium in electric field, and of course we are dealing here with a static electric field and electric polarization, and we will introduce a new vector called electric displacement vector, and then we will have a relationship between these three vectors: displacement vector, electric field vector and polarization vector. And then we will discuss about the capacitance of different types of capacitors and how a dielectric material is enhancing the capacitance of a capacitor when it is inserted between the plates of the capacitor. Suppose we have two parallel plates like a capacitor in which we have free charges, so that there exists an uniform electric field, and if we put a dielectric material in this uniform field, what happens that there is a polarization in the dielectric material. One surface becomes positively charged, another surface becomes negatively charged. This occurs either due to stretching or due to rotation. As we discussed in the last class, suppose these are the molecules or atoms whose center of positive charge and center of negative charge generally they coincide if they are non-polar molecules, but when we apply electric field, this center of positive charge and center of negative charge they get shifted like this, and the adjacent atoms they cancel these positive negative charges, while at the surface, one end of the surface and at the other end of the surface there is net charges developed, which create or which develop an electric polarization. This is first in the case of non-polar molecules due to stretching. But if the molecules are polar molecules, these polar molecules have inbuilt dipole moment. Their center of positive charge and center of negative charges they are being already separated. Okay? But the net dipole moment of this substance is 0 because of the random distribution of these dipole moments. These dipole moments are randomly distributed inside the material. So, the net dipole moment is 0. But when we apply an electric field to this dielectric material, because of the electric field these polar molecules that rotate and they tend to line up in the field direction. So, what happens again, the result is same. So, these dipoles they get oriented in the field direction So, again the adjacent atoms inside the substance they cancel the charges positive negative, but there is uncancelled positive charge at one end of the surface and negative charge at the other end of the surface. So, that creates electric polarization. So, the substance develops a net dipole moment when it is subjected to an external electric field, and this dipole moment developed per unit volume is represented by a vector called electric polarization. Electric polarization. So, this electric polarization is the dipole moment per unit volume of the substance. If delta V is the volume of the substance in which the dipole moment developed is delta P, then per unit volume the dipole moment developed is delta P by delta P, and that is polarization vector P. So, if we consider, it is rather better to write tau instead of V to avoid the confusion between the potential, electric potential. So, tau is the volume element. So, if a dielectric material is already polarized and if we consider a very small volume element d tau of this dielectric material, then the total dipole moment of this volume element should be P into d tau, because P is the dipole moment per unit volume. So, in the volume d tau, the total dipole moment is P into d tau. Okay. Now, let us calculate the potential due to a polarized dielectric material. Suppose we have a dielectric material which is already polarized, and let us consider a small volume element d tau of this dielectric material, and at a vector r we want to find out what is the electric potential. So, this point is A. Okay. The source charge is here at d tau. Because of this we want to find out the potential at A. As we have already discussed before, that due to an electric dipole of dipole moment P, the potential at a distance r is V is equal to 1 by 4 pi epsilon naught r dot vector P by r square. This is the formula we have already developed, we have already derived the potential due to dipole of dipole moment P. Now, if we are considering here a volume element d tau of the polarized material, then this d tau volume element has a dipole moment, and obviously it is P into d tau. Okay. This is capital P into d tau, where capital P is the polarization, it is the dipole moment per unit volume. So, this into d tau gives you the dipole moment of this volume element d tau. So, instead of P we will write here, or P dipole moment P will be replaced by capital P into d tau. So, the potential here due to d tau element should be dV. Okay. So, dV is now equal to 1 by 4 pi epsilon naught r cap dot capital P into d tau by r square. So, if we want to find the potential due to the entire polarized material, we have to integrate it. Hence, the potential due to the polarized material is B is equal to 1 by 4 pi epsilon naught integration of r cap dot vector P by r square d tau. The integration is over the volume tau. Okay. Or this we can write as 1 by 4 pi epsilon naught integration over the tau volume P dot r cap by r square into d tau. This is equation 1. Okay. From vector identity vector algebra, we know that gradient of 1 by r is equal to minus r cap by r square. This we have already derived before. We have discussed in the vector algebra that gradient of 1 by r is equal to minus r cap by r square. So, this r cap by r square should be replaced by minus gradient of 1 by r. But remember, while taking the derivative here, it is the derivative with respect to the origin, but here the derivative is taken from the with respect to the source charge. therefore, the direction r is reversed. So, here we will not take this negative sign, and for r cap by r square we can write here gradient of 1 by r. Hence, our equation 1 will become V is equal to 1 by 4 pi epsilon naught integration over volume tau p dot gradient of 1 by r d tau. Let this is equation 2 now. Again we will use another vector identity, that is divergence of a scalar into a vector. Here 1 by r is the scalar, r is the magnitude of position vector r, p is the vector. Divergence of a scalar into a vector is equal to scalar into divergence of the vector plus gradient of the scalar dot vector p, okay, which is this one, gradient of 1 by r dot p or p dot gradient of 1 by r. Therefore, gradient of 1 by r dot p or p dot, this implies, or p dot gradient of 1 by r is equal to divergence of p by r minus 1 by r into divergence of p. Okay. So, in equation 2, instead of, in place of p dot gradient of 1 by r, we will put divergence of p by r minus 1 by r into divergence of p. Hence, our equation 2 becomes now V is equal to 1 by 4 pi epsilon naught integration over tau, this is now divergence of p by r d tau minus integration 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught integration of divergence of p by r d tau, of course. Okay. This is now a volume integral, and we will use a theorem in vector algebra called Gauss divergence theorem. According to Gauss divergence theorem, the surface integral of a vector is equal to divergence of its volume integral. Okay. So, we will convert this volume integral to a surface integral. Okay. Of course, this surface is a closed surface that encloses this volume tau. Okay. Now, using Gauss divergence theorem, using Gauss divergence theorem, we have V is equal to now 1 by 4 pi epsilon naught into divergence of, sorry, not divergence, only it becomes the surface integral around the closed surface p d tau divided by r, and plus this we can write the second term as 1 by 4 pi epsilon naught integration over tau divergence of p by minus divergence of p by r d tau. Okay. I write it here plus minus sign, I took it inside the integration, or this we can write as V is equal to 1 by 4 pi epsilon naught integration over surface S p d tau divided by r plus 1 by 4 pi epsilon naught integration over d tau minus divergence of P d tau divided by R. So, this is equation 3. So, this equation looks like the potential is consisting of two terms. The first term is like this one, it is due to a surface charge distribution, and the second term is due to a volume charge distribution. And remember, here our charges are not free charges. In the dielectric metal, these charges are bound to the surface of the volume. So, these are the bound charge distributions. So, we can write this this should be ds now. It is no more tau. Once it is surface integral, it should be ds, or we can write d sigma, where sigma is the surface. Whatever, it is better write ds. Okay, because the volume integral is converted into now surface integral using Gauss divergence theorem. So, this is like our surface charge density sigma B. Sigma we write surface charge density, that is the charge per unit area. I write a subscript B here to indicate that this is a bound charge. So, this is sigma B into ds integration gives you the total charge, surface charge density integration over the surface, and this one is like a volume charge density rho. Of course, I should write a subscript B to mention that it is a bound charge. So, it is a volume charge density. This contribution is due to volume charge density. This rho B into d tau integration is the total charge. Okay. Therefore, this equation 3 shows that in a dielectric material, when the material becomes polarized, we have a surface charge density sigma B is equal to P dot n cap. Of course, this ds we should write it as P dot ds, and it is ds is n cap ds. So, it is P dot n cap. Okay. And the volume charge density of this polarized material is equal to rho V, which is equal to minus divergence of V. Okay. So, these are two important conclusions we got regarding a polarized dielectric material. Now, let us write our Gauss law in a dielectric material. Our Gauss law says, in the differential form, the Gauss law is divergence of electric field E is equal to rho by epsilon naught. Here rho is our volume charge density, and this volume charge density is about what kind of charge? It may be any kind of charge. It may consist of free charges as well as bound charges. Suppose there is a region where charges are embedded in a dielectric metal or bound charges in the dielectric metal, and of course, there may be conductors where free charges reside. So, they totally contribute to this rho. So, we can write that this rho has two parts, one is free charge density plus another is bound charge density. Rho is equal to rho f plus rho b. Then our Gauss law becomes divergence of E is equal to now rho f plus rho b divided by epsilon naught is equal to rho f by epsilon naught plus rho b by epsilon naught. Okay. And what is this rho b? We have already derived that it is minus divergence of P, where P is the electric polarization vector. So, our divergence of E becomes rho f by epsilon naught plus minus divergence of P. So, it is minus divergence of P by epsilon naught, or multiplying epsilon naught this side, we get epsilon naught into divergence of E plus divergence of P is equal to our rho f by epsilon naught. So, again here there should not be epsilon naught, because we have multiplied epsilon naught to each term. So, this should be only rho f, okay. Or we have in these two terms we can take divergence of epsilon naught E plus P is equal to rho f. So, we express Gauss law in the presence of dielectric by an analogous equation. Just the electric field E is replaced by a factor epsilon naught plus epsilon naught times E plus polarization vector P, while this charge density is only the free charge density. Okay. So, this term in the bracket is defined as a new vector called electric displacement vector as D, which is equal to epsilon naught E plus P. This is called electric displacement vector. D is called electric displacement vector. When there is no dielectric material, there is no polarization, and our displacement vector becomes epsilon naught into E. Okay. So, we now introduced three vectors: electric field vector, polarization vector and displacement vector. Okay. And Gauss law in dielectrics now becomes divergence of this is our displacement vector, divergence of D is equal to rho f. So, Gauss law without dielectric is divergence of E is equal to rho by epsilon naught. Here rho is any charge density, while in dielectric material we write divergence of D is equal to rho, but this rho is only free charge density. Okay. This is Gauss law in dielectric. Gauss law in dielectric material. So, we can see that these three vectors have quite physical significance as far as the overall electrical response of a dielectric material to the electric field is concerned. Let us visualize it. Suppose we have a dielectric material like this, and we have two parallel plates in which we have given free charges, so that there exists a uniform electric field from between these two plates. So, before introducing this dielectric material, the field lines were like this. Okay. These are the field lines. But once we introduce the dielectric material between these plates, we have introduced the dielectric material now. Now, this dielectric material gets polarized because of the electric field, so that some polarized charges are developed at the two opposite faces of the dielectric. As I have already discussed, because of the electric field, positive charges are pushed towards this surface, negative charges to the other surface. Okay. But this polarization is never complete, as that happens in case of a conductor, where there are enormous free charges. They move until they cancel the applied field, so that they do not allow field to pass through them. Conductors do not allow field to pass through them. The field inside a conductor is 0, but here this polarization is never complete. Okay. So, what happens due to this polarization, an electric field is induced inside the dielectric material in opposite direction to the applied field, but it is quite less than the applied field. So, inside the dielectric field, now what happens, the electric field is reduced. If our outside electric field, outside the dielectric, electric field is E naught, and because of the polarization there is a reduced electric field now, and say this is now like this. Okay. So, inside the dielectric metal now electric field is reduced, and inside the dielectric metal, say it is the field is E I, then this E I, the field inside the dielectric material divided or and field outside the dielectric metal is E O. This E O by E I is a constant. This ratio is called dielectric constant, dielectric constant of the material, Okay. And the line from this point to this point, okay, if we continue these lines, these are being the lines from the free charges, joining the free charges. They are originated from the free charge, end at the free charge, and that is the lines of electric displacement vector, because their source is free charge, while electric field is due to any charge. Here it is due to bound charge, here it is due to free charge. So, if lines are continued from this point to this point, then these are D lines, displacement lines, while the lines outside the dielectric as well as inside the dielectric are the field lines. Okay. And due to this polarization, the field induced inside the dielectric is opposite to the applied field, therefore, the net field decreases, and if this net field inside the material is E I and field outside the material is E O or applied field is E O, then E O by E I is equal to K. So, the field reduces by K times. Okay. So, we can write the field inside a dielectric material becomes 1 by K times the field applied across it. Okay. So, this is the physical significance and the relationship between the three vectors: displacement vector, electric polarization vector and electric field vector. Okay. Now, let us consider a dielectric material. We call them as a linear isotropic dielectric material. Why linear? Because in these materials our electric polarization depends directly upon electric field, because if we apply more electric field, more force stretches the polar non-polar molecules, so that polarization will be more, or in case of polar molecules they get more torque, so the line of or orientation along the field will be more. Therefore, the combined effect is that if we apply, if we increase the applied electric field, then the electric polarization will increase, and if in a material our electric polarization vector is directly proportional to applied electric field E, then this material is called linear dielectric, and in this case our polarization vector becomes equal to P is equal to epsilon naught into chi subscript E into electric field E. Here chi E, chi subscript E is called electric susceptibility. Electric susceptibility. Electric susceptibility. Here the subscript E is introduced for differentiating it from magnetic susceptibility, because we will discuss later in magnetism that there is a magnetic susceptibility of different materials, and it is here electrical susceptibility. And susceptibility, as we can interpret in a literary way, that it is just the sensitivity, it is almost a measure of sensitivity of the material to the external field. So, if the material is more sensitive to the field, it will create more polarization, less the sensitivity, less the polarization. So, the susceptibility is a measure of how much to what extent the material can be polarized. Okay. And this equation, the material that satisfies, the material that obeys or satisfies this relation is called a linear dielectric. And when we say it is isotropic, means its susceptibility is not a function of direction. In any direction the material shows the same susceptibility. Okay. This is called a linear dielectric. Now, our displacement vector d, as we know, is equal to epsilon naught E plus electric polarization P. So, in place of P, from equation 1 we write it is epsilon naught chi into E. So, our d becomes epsilon naught into E plus epsilon naught chi E into E, or d is equal to epsilon naught into 1 plus chi E into E. This is equation 2. This is the relationship between displacement vector and electric vector. And we write this epsilon naught into 1 plus chi E as epsilon, which is the permittivity of this dielectric material, permittivity of the dielectric material, absolute permittivity of this dielectric material. So, our d becomes epsilon into E. This is the relationship between displacement vector and electric field vector, say equation 3. And from this equation, our 1 plus chi is equal to epsilon by epsilon naught, which is called relative permittivity or dielectric constant. It is relative permittivity or dielectric constant of the material. So, these are the relationship between electric displacement vector, electric field vector, permittivity, susceptibility, relative permittivity, dielectric constant. So, they all determine the electrical behavior of a dielectric material. Okay. We will see that what happens when a dielectric material is introduced between the plates of a capacitor. Earlier we have discussed what is a capacitor. It is a device to store electric charge in a minimum volume, and generally it consists of two conducting bodies or two conductors separated by an insulating medium. And those cases we have discussed, in that case we have taken only the air gap between the plates. Now, we will see if that air gap is replaced by a dielectric material or some dielectric material of some thickness is introduced between the plates of the capacitor, what will happen, what will happen to the capacitance of the capacitor. So, let us start with a parallel plate capacitor. As I told earlier that capacitance of a capacitor depends upon the shape and geometry of the conductors, and if they consist of two parallel plates separated by an insulating gap, it is called a parallel plate capacitor. If it consists of two conducting spheres separated by an insulating gap, it is called a spherical capacitor, and if it is consisting of two coaxial conducting cylinders separated by an insulating medium, it is called a cylindrical capacitor. And in case of a parallel plate capacitor, we have derived earlier the capacitance value of its capacitance when the plates are separated by air gap. So, we will consider a parallel plate capacitor parallel plate capacitor with dielectric material. Okay. Suppose this is a parallel plate capacitor consisting of two parallel conducting plates separated by a distance d, and if the gap between them is air, and if we have given charge plus q to this side minus q to the other side, uniform electric field exists between the plates, and using Gauss law we have calculated that electric field is sigma by epsilon naught, where sigma is the surface charge density. If the plate area is A, then surface charge density is charged by area A, that is by epsilon naught, is equal to q by epsilon naught into A. This is electric field, and the potential difference V is field into distance, because it is uniform field. Potential is the negative field is the negative gradient of potential, and potential is the line integral of field. In case of uniform field, it is field into the separation E into d, and it is equal to q by epsilon A into d. So, the capacitance of the capacitor C is equal to charge stored by potential difference, that is equal to now here epsilon A by d. This is the capacitance of the parallel plate capacitor when the gap between the plates is filled with air. Suppose now we introduce a dielectric material of thickness T, a dielectric material of thickness T between the plates of the capacitor. Okay. So, our air gap is now d minus T. The thickness of dielectric material is equal to T, and its dielectric constant is say K. Okay. So, the air gap is now d minus T. Okay. So, the potential difference between the plates is now the potential difference in the air gap plus potential between the surfaces of the dielectric. So, potential between the surfaces of the dielectric is now the field inside the dielectric, say it is E I, field inside the dielectric is now reduced. How many times it is reduced? It is reduced by k times. Already we have discussed that when a dielectric material is introduced between the in an electric field, because of the polarization, the field inside the dielectric is reduced by a factor k, which is the dielectric constant of that material. So, the potential difference between the two surfaces of the dielectric is now E I into T, field into distance, field into thickness, and E I is 1 by k times our E naught by applied field or existing field, which is q by epsilon naught into A. This is our field inside the dielectric. This into the thickness of the dielectric is the potential difference between the two surfaces of the dielectric, and the rest potential difference is this potential difference plus this potential difference is the total potential difference in the air gap, which is equal to the field, that is q by epsilon naught A into the air gap is d minus T. So, this is our total potential difference, or this is equal to now q into q by epsilon naught A taking common d minus T plus T by K. Okay. So, the capacitance of this capacitor is C is equal to q by V is equal to now how much? Epsilon naught A comes to this side by divided by d minus T plus T by K. So, this is the capacitance of a parallel plate capacitor when a dielectric material of thickness T is introduced between the plates. Okay. So, our C is, we can write it as epsilon naught A by, in the denominator the LCM is k, and it is k into d minus t plus t, or C is equal to epsilon naught or k into epsilon naught A by d minus t into k plus t. This is the capacitance of a parallel plate capacitor when a dielectric material of thickness T is introduced between its plates. Okay. Now, if the entire gap between the plates is filled with dielectric, if the entire gap is filled with dielectric, then T is equal to D. This thickness T of the dielectric will become equal to D, and the above equation, putting T is equal to D, we get C is equal to k into epsilon naught A by k into d minus d plus d. This is 0. So, or C is equal to now k into epsilon naught A by d. Okay. So, let this C we write as C dash to distinguish it the capacitance of the parallel plate capacitor when the plates are separated by only air gap. So, you can see that C dash by C is equal to k, or C dash is equal to k into C. That means, the introduction or filling of the dielectric material between the plates of the capacitor is enhancing its capacitance, and the capacitance is increasing by k times, where k is the dielectric constant of the material. So, we should, to have a higher capacitance or a better capacitor, we should fill the plates, we should fill the gap between the plates of a capacitor with materials of very high dielectric constants. So, always the materials having very high dielectric constants are found applications in designing a capacitor. Often we use our mica as a good dielectric material between the plates of a capacitor. Of course, there are a special kind of materials called ferroelectric materials which have very high dielectric constants. There are ferroelectric materials often used in industry. They are barium titanate, lead zirconium titanate, popularly known as PJT. These are the materials we use in the capacitors to increase the capacitance of the capacitors. Okay. So, this is the capacitance of a parallel plate capacitor. Let us calculate the capacitance of a spherical capacitor. So, now at least up to this we get one conclusion that once we calculate the capacitance of a capacitor with air gap, and we want to then find out the capacitance of the capacitor with dielectric inside it, we have to simply multiply by k. The capacitance should be multiplied by k. Okay. So, let us consider the capacitance of a spherical capacitor. This spherical capacitor is consisting of two concentric spheres, conducting spheres of radius r1 r2, say r1 is the radius of the inner sphere, r2 is the radius of the outer sphere, and if we give charge plus q to the inner surface, inner sphere, that will of course induce minus q charge on the outer sphere. Then an electric field exists between the two spheres, and at a distance r, say at a distance r from the center, applying Gauss law, we can find the electric field E is equal to 1 by 4 pi epsilon naught q by r square. I have already discussed it, that the electric field due to a spherical charge distribution outside the charge distribution is 1 by 4 pi epsilon naught q by r square. Okay. So, if you want to find the potential difference between the two surfaces, then this B must be is equal to negative of the line integral minus A dr from R1 to R2, okay, is equal to minus integration of, okay, this integration should be from R2 to R1 because the outer sphere is at lower potential, it is at the negative charge, and the inner sphere is at the higher potential with a positive charge. Okay. Then it is equal to minus 1 by 4 pi epsilon naught q by r square dr integration from R2 to R1 is equal to 1 by q by 4 pi epsilon naught taken outside the integration, 1 by r square integration is minus 1 by r, minus minus this becomes plus 1 by r from R2 to R1 is equal to q by 4 pi epsilon naught into 1 by R1 minus 1 by R2 is equal to q by 4 pi epsilon naught into R2 minus R1 by R1 into R2, or the capacitance C, which is equal to q by 4 pi epsilon naught, sorry, the capacitance of the capacitor is C is equal to charge by potential difference q by V. From this equation q by V becomes equal to 4 pi epsilon naught into R1 R2 divided by R2 minus R1. This is the capacitance of a spherical capacitor when the space between the spheres is filled with air. If the gap is filled with dielectric, the capacitance will increase by k times, as we have already discussed. So, with dielectric the capacitance will become 4 pi epsilon naught k into R1 R2 divided by R2 minus R1. Okay. So, this is the capacitance of a spherical capacitor without and with dielectric. Okay. So far we have discussed what are the electrical response of different materials to the external electric field, and we came across with a new quantity called electric polarization and a new vector electric displacement vector. They have enormous physical significance, and we can see it later while developing Maxwell's electromagnetic wave equations. We use these quantities often. Okay. Thank you.